So let's talk a little bit about correlation involving two variables. We're looking at bivariate data and how are the variables related. So what we have here is a scatter plot of some data I took from old classes, and students gave me their heights and their weights, and I guess based on that, you could think about what we've thought about this quarter, and we could maybe say, there's some bias there. Is there not bias there? Are they actually measuring their exact weight and their exact height? Are they estimating? Are they underestimating, overestimating? Who knows? One thing we could look at, we've got a lot of data points right here, right on the line of 150, right on the line of 200, right on the line of 250, one right on the line of 100. Something we might say is, when you ask people how much they weigh, they're not going to say, I weigh 123 or I weigh 146.8. They say, I weigh 150, I weigh 175, I weigh 200. Nice even number. So maybe there's some bias there. For the longest time, I thought I was 6'2", and in fact, I'm not quite 5'10". So, so the data may be skewed. Anyway, things that we've been talking about. Now we can plot this data, height versus weight, and we can look at the relationship between height and weight. Now we might say, I think the taller someone is, the more they weigh, the taller they are, the shorter they are, the less they weigh, things like that. So what I did, I just plotted this data, and what we can see is, kind of generally, you get this sort of things are going up as heights get bigger, as people get taller, weights go up. So there seems to be some sort of relationship. And what we can do is we can calculate a correlation coefficient. Okay, so I did that for this data, and I get an R of 0.544. Okay, so it's positive correlation, which means, as we can see, as X gets bigger, Y gets bigger. Okay, now is this a strong correlation? Not so strong? Well, what we could do is we could use table A6, critical values of the Pearson correlation coefficient, and we're not going to be doing this necessarily, but if we did a hypothesis test where the null hypothesis was no linear correlation and the alternative was yes linear correlation, we could use this table. So the data that I actually used has 192 pairs of data. So we look at n, that's how many pairs of data you're looking at. So we've got 100 here. And what this is for alpha 0.05, for what we've been using throughout the quarter, the critical values would be plus or minus 0.196. So since we've got an R value of 0.544, this is greater than the critical value 0.196. So we would reject the null and say, yeah, there seems to be some evidence of linear correlation. Okay, you can see that there's some linear correlation. Just when we originally looked at it, it looks like things are going up to the right, down to the left. So, and then another thing we can do is let's find the coefficient of determination, which is R squared. So we simply take 0.544, our value, square it, and we get 0.296. And what this tells us is that the linear correlation between the two variables accounts for 29.6% of the overall variation. So if we created a linear model describing this, the variation from what we would expect, 30% of it basically is defined by the relationship between the two variables, height and weight. Okay? And the higher that value of r squared, the more the variation is determined by the model, so the actual relationships between the two variables. Let's look at another set of data. So this data kind of goes the other way, and it has an R value of negative 0.537. So again, it looks like, you know, it's going from bottom right to upper left-ish. So there seems to be some correlation. As x gets bigger, y gets smaller. As x gets smaller, y gets bigger. So the R value here of negative 0.537. Again, we've got about 180, 190 pairs of data. If we look at our table of critical values, again, it's plus or minus 0.196. Again, we've got the value of negative 0.537, which is beyond the critical value. So we could say there's some evidence of linear correlation in these two variables, x and y. Coefficient of determination, 0.288. So 28.8% of the overall variation of the y values can be explained by the relationship between x and y. And then we've got a last data set that looks something like this. Things just kind of seem random. They're sort of spread out, no real pattern. And we've got an R value of negative 0.049. Relatively small. Again, if we looked at our critical value plus or minus 0.196, this R is between those two. There doesn't seem to be any, so we would fail to reject the null hypothesis. And it doesn't seem that there's any evidence that there's any linear correlation between these two variables. And the R squared is 0.0024, which means that less than 1% of the variation is explained by the relationship between the two variables. Again, the higher the R squared, the more the variation in y is based on the relationship between the two variables, or we could say it might suggest that there's stronger linear correlation between the two. So basically, looking at these three graphs, this one seems to have, you know, we could maybe say that there's some linear relationship between height and weight here. Maybe there's some linear correlation between these two variables, and here there's nothing really. That, you know, things are pretty random. So that's R and R squared.